All right. Well, thank you everyone for taking your seats. Excited for our next presentation with Nik Chekshin, and it's entitled Energy Efficiency to Mitigate Industrial Carbon Emissions. And Nik Chekshin is the founder of Anselm and a doctoral researcher with Scripps Research, working at the interface of synthetic, medicinal, and computational chemistry. So excited for this presentation. Thank you, Nik.
Thanks everyone for coming today, and it will be a tough act to follow after a very entertaining Ravi's talk. Mine is a bit more technical, as Ravi said. You go too technical, no one can remember no one can remember anything. But I hope for my talk you will get some takeaway messages. And I will talk about how initially I was going to talk about energy efficiency in a very broad sense, but then I decided to focus a bit more on where potentially we can make most impact, and that's where Anselm actually is focusing on, is the industrial sector. So we'll start with a bit of an overview of the background. So as we all know, there are goals set for decarbonizing, for reaching net zero by 2050. And actually, right now, if you look across different sectors, the industrial sector in the US is considered one of the most difficult to decarbonize, and also one of the most carbon intensive. Actually accounts for about a third of all of the carbon emissions in the US. And then if we take a step back, actually look where right now the energy consumption is, and look into the energy mix, to say. We have a split between oil and gas and coal, and as you can see, the bottom parts of the graph is where essentially that is, right? So the red and the red is oil, and the yellow is coal, and then you have your blue, which is gas. And if we look into the split in terms of where it's coming from, actually in the US, 84% of energy is still coming from fossil fuels. By comparison, in the EU, it's only about 60%. So we are definitely not ahead of the world in that sense. And right now, only about 16% is coming from low carbon sources. So still quite a lot is accounted for by fossil fuels. I would say, obviously, China is one of the biggest contributors in terms of coal right now. And there is a big drive. There are reasons for that. But right now in the US, after the big drive to move coal, actually, we've managed to remove the majority of coal that is used right now down to 12%. And as you can see right now, actually, the renewable sources account for only about, they're only here right at the very top, the very thin layer up there, which accounts for just a small fraction, only 16% in total. And the little dip you see over there is the COVID. So during the COVID, the energy use went down. If we look into electricity production, actually where that's coming from, actually about 62% of electricity is accounting for fossil fuels still, and only 28% for renewables. So the global drive for electrification, switching to electric vehicles, still, if we look into not just scope 1, which is what's coming out of the tailpipe, but full life cycle emissions, scope 2, scope 3, a lot of the electricity is still produced by burning natural gas and by burning coal. And here, what I'm showing is progression through the years, right? As you can see, there's been a drive in reducing the amount of coal and amount of oil that is used in the US, especially on the left-hand side, that's the absolute values, and on the right, have the percentage. You can see how dramatically the percentage has dropped over the past 40 years, from 60% coal down to about 30% coal in electricity production. But still, 61% of electricity is produced from fossil fuels. And now, what if we look into the total energy use, right? So that's where efficiency essentially comes from. So in 2021, that is data by the EIA, by the way, consumed 97 quadrillions of energy. And how was it used? So if we look into the split, actually about 37% was accounted for by transportation, 35% in the industrial sector, and only 16 residential and 12 commercial. But what's quite striking, I think, is over 2/3 of that energy was actually wasted. That's data from the Livermore National Labs. It was rejected. So as you can see, the sectors, the dark blue is what was actually used, and the light blue is what was wasted. And you can see by percentage, quite remarkable. In transportation, we waste actually a vast majority of energy, and that's through heat, through dissipation, through all the inefficiencies that come. If you assumed you cannot have 100% efficient machine, right? So you're always going to waste. But actually, while in transportation it's hard to address, obviously there are continuous improvement in efficiencies in new vehicles. In industrial sector, you would imagine it's been addressed a long while ago, but still about a half of energy is still rejected. So it's a big problem. And if we look into the projections, actually, right now, if we look from what EIA estimates into, well, all the way down to 2050, the energy consumption is only going to grow. So it's not really expected that we are going to have less consumption, especially the industrial sector, as you can see, is one of the biggest. And in terms of the energy use in total, you can see that renewable energy, of course, is projected to grow. That is the brown line on the right-hand side. But if you look into so biofuels, by the way, is all the way down there at the bottom. So it's it's a bit hard to point. Yeah, all the way down there, the green line on the graph. But actually, if we look into natural gas and liquid fuels, they're not really projected to drop that much. So EA is clearly not expecting them to go away very quickly. If we look into the emissions, yeah, of course, we are expecting to have them drop down, but there are obviously a variety of scenarios. The optimistic one is that we are going to drop down by about 30%. That's, by the way, nowhere near net zero yet. And actually, the less optimistic one is that we will drop a little bit, but we'll actually, with the increased energy consumption, will still come back. So the projections are not as optimistic as you might think. Now the okay, now it's loaded. The DOE, the Department of Energy, has issued an industrial decarbonization roadmap where they've outlined the key approaches to decarbonization, how to tackle those the carbon emissions that come from the industrial sector. And the 4 key pillars were identified as the energy efficiency, electrification, LCFF-EES, which is low carbon fuels and feedstocks, and then carbon capture, utilization and storage, CCUS. But they highlighted that actually energy efficiency is one of the key pillars to achieve the fastest decarbonization right now, because obviously carbon capture, low carbon fuels, those are great, but they take very long times to implement, large investments. Whereas with addressing the inefficiencies that exist right now, that is the most viable approach to reducing the immediate emissions. And the recommendations from DOE actually highlight that we need to advance early stage R&D in energy efficiency, and we need to address the process heating efficiency across the industrial sector. That's where most of the inefficiencies are, in the waste heat. We need to invest in multiple process strategies, integrate the solutions, and conduct complex modeling and analysis to actually identify where those inefficiencies are so that we know how to address them. And we need to obviously engage the communities and develop the thriving workforce, scale through the demonstrations and so on. So there are multiple approaches, but energy efficiency is highlighted as one of the key ones. If we look at the impact, the projected impact on industrial CO2 emissions, actually energy efficiency here is showing in red. It's expected to amount obviously to quite a lot. That's the optimistic, so to say, scenario, the net zero by 2050. If you look at the closest one, by 2030, you can see energy efficiency is expected to amount to basically more reduction in CO2 than all other approaches combined. So in blue, you have carbon capture, and then in green, it's the low carbon fuels. And then we also have, I believe, electrification in that one as well. So right now, it's like I said, it's clearly, if we want to take fast action, energy efficiency is going to be the biggest impact. And if we look actually how energy consumption is distributed in the industrial sector, there's a lot of numbers here, but I'm just going to outline the main trends. Like I said, about a third of the energy consumption is accounted for by the industrial sector. And if we look at the split, actually, most energy intensive sectors of the industrial consumption amounts to the most emissions, which does actually make sense. Now, if I switch, so between these two, here we have the CO2, and here we have the energy consumption. So you can see all of the proportions are actually very similar. So the third of the energy consumption by the industrial sector translates to about a third in CO2 emissions. And if we look into where those emissions are coming from, vast majority actually coming from here. We have chemicals, chemical production, and refining. That amounts to a vast majority of the total industrial emissions, right? So, and why is that? So the answer is because these are the most energy intensive processes, right? So that's where you have to supply a lot of heat, which means you waste actually a lot of heat as well. On the diagram at the bottom, you can see that the majority of energy consumption is actually process heat. It's so hard to point. Yeah, so over a half of energy consumption is in process heat. What I'm showing on the left here as well is how the energy consumption is distributed between different processes. The higher, basically the take-home message is the higher the temperature, the more waste you have. And that's why refining is way more than, for example, food production. And again, if we turn to EIA in terms of the projections, everyone is talking about how we have to move away from fossil fuels. Well, clearly, we are not really expecting much of a drop. So petroleum and liquid consumption is expected to, if not stay the same, it's actually even expected to grow a little bit in a less optimistic scenario. And then if we look into how that's going to affect the production right now, we know in the US, especially many of the refineries are under tremendous pressure to decarbonize. So they are running out of business or transitioning to biofuel production. But you can see that the demand for petroleum products and the production is going to, if not stay the same, then it's expected to also grow under the high economic, high gas supply scenario. Then how does that translate to emissions? Well, first here I'm showing actually the adoption of liquid fuels. Everyone is very excited about biofuels, right? But the truth is that the supply is so much smaller that the proportion of fuels that you get from your oil or from fat from biofeedstocks is going to be just peanuts compared to what you can get from petroleum still. So there are projects like, for example, Phillips 66 is converting their Rodeo refinery. It's called the Rodeo Renewed project. The full facility, almost 200,000 barrels a day capacity, they're converting completely to biostocks, right? The capacity will actually be down from 100% down to 15%. So that is the highest that they can produce, just because there is not enough supply of feedstocks. And if we look into crude oil, I just wanted to highlight here, it's not really going away. The yellow line here, it's actually expected to be in high demand. If you could give me a warning whenever it's 10 minutes or 15 minutes. Okay, great. So how does that translate to emissions? So as you see, I've been sort of following this funnel, focusing down on the biggest emission source. We started with the whole consumption of energy, right? And then we focused on the industrial sector, and then we narrowed it down to who are the biggest contributors, as we see refineries and chemical production plants. Actually, refining industry is right now the third largest stationary emitter of CO2 worldwide. It amounts to, well, in 2018 was 4%. Right now it's about 6% of global CO2 emissions. And another thing to note is that over the past 20 years, the emissions from refineries globally rose by about a quarter of what we had. If we continue that trend right now on the projections that we have, it's going to be, it's cumulatively going to amount to over 16 gigatons of CO2 by 2030. And in terms of the projections, you can see that clearly there is an expectation that from, so the one at the top is coal, that is going to drop, of course. Then petroleum is right here in blue. And then you also have electricity that's coming down because of wind and solar that is getting integrated. The carbon emissions from the petrochemical industry by 2050, even though there is all this talk about net zero, is not expected to really drop that much. So what can we do about it, right? Here I wanted to also highlight that net zero assumes 38% more energy efficient refining industry. It's an assumption, but 38% is actually quite a lot from where we are right now. And guess how much improvement has been seen in the past 20 years? Barely over 12 to 15% is the average industry standard. And right now you can see that they are struggling to improve. So there are, as you can see, there's a huge spread in these scenarios. We are all the way from nearly net zero to basically barely reducing anything from where we are. And the reason there is such a big spread is there is a lot of uncertainty. No one knows what is coming. So no one knows actually what scenario we are going to follow. But what we know for sure is that the demand for fuels is not going to decrease, it's actually going to grow. So I'll drop, so here we have a bunch of data. I guess I won't really go into too much detail. I guess the biggest message here is just to say that if we look into refineries, most emissions come from large point sources, but the more complex the facility is, the harder it is to identify where actually your most inefficient equipment is. And very often, right now, what happens is the manufacturers, they have this budget to decarbonize, so they invest into buying a more efficient furnace or buying a more efficient heat exchanger. But very often what happens is actually they end up reducing emissions by a little bit, but they ramp up their production, so the overall emissions don't decrease as much because of the systematic inefficiencies that remain unaddressed. And then here, here I just wanted to compare where we are right now. If we look into the carbon intensity now, really focusing on the refining by different companies here, they are ranked by carbon intensity. So you can see that some of the worldwide companies, Gazprom is obviously all the way up there. There hasn't been much investment into energy efficiency. But for example, Phillips 66, yellow, you can see here, has really grown up with ramping up of that production capacity. And then we have basically, if you look in comparison, Valero, Chevron, they are all up there. And it hasn't really, I mean, there are some improvements, but it hasn't really improved as much. And Exxon, I believe, is from here. Oh, yeah. Exxon is right down here. But the thing is, their capacity is obviously much smaller. And all of these facilities, by the way, right here, we have, so with Valero is the Port Arthur refinery. Look at this. Baytown and Baton Rouge refinery from ExxonMobil are the highest in carbon intensity. And right now, there is very little investment into actually decarbonizing them. So everyone is pouring money into carbon capture, whereas the biggest efficiency in yellow, that is actually what can be addressed through energy efficiency, the biggest source of the emissions that they have. And here, again, another complex graph. To make it less confusing is to say that majority of facilities in the US, actually over 3/4 of petroleum and refining facilities in the US are over 75 years old. They're very old. There hasn't been a new refinery built in probably nearly 50 years. There are some biorefineries that are getting built, but I already mentioned that the capacity is way smaller and the fuel demand is growing. Actually, right now in California, there is the pressure on fuel producers is so high that it's becoming not even profitable to produce fuel. So we all see huge gas prices keep increasing. Well, right now I can tell you the trend is that they are only going to keep increasing because Right now, California, out of the store that you're paying per gallon, $1.2 is taken immediately out by the state. So if you take that into account, actually that brings it down to about $3.5. So that's actually comparable to what you have, in other states. And another big thing is that right now everyone is so excited about electric vehicles and transitioning from petroleum to electricity. But the questions are, first, what is the carbon footprint of the electricity that you have there? And second, what about the lithium, right? All the batteries, vehicles, they wear out, they end up in landfill. And then how many emissions are produced through the production of lithium? So look into life cycle emissions. Actually, an electric vehicle right now produces more emissions, even though you have none coming out of the tailpipe, more emissions than some quite efficient petroleum-driven vehicle. So I went a little bit off this there, but the point of this slide was that a lot of refineries are very old and they are highly complex. So here the graph is comparing deep processing versus shallow processing facilities. If you look by the country, most refineries built in Asia are actually quite modern. They are not more than 20 to 30 years old, which means they're highly integrated, they're highly efficient. Whereas in the US, the deep refineries produce 6 times more emissions. They are harder to optimize. And actually, the proportion of deep refineries, I mean, 3/4 of them are not only old, but also deep processing. So it's very hard to analyze and see how to actually optimize their efficiency. And clearly, we're going to rely on them, right? So 80% of whatever surrounds you is made from petroleum products. So it's not going to go away, and it's a big driver of the economy. The question is, how do we address the big problem of carbon emissions that can perhaps be avoided but cannot be fully captured? How much time do I have? 5 minutes? Okay. I guess I'm gonna. So where are we going from this? So we have obviously all the politicians who say in California with the California scoping plan. Is any one of you familiar with that? No. So the California scoping plan is essentially assuming that by 2030 we're going to have a certain reduction in emissions and it's in fossil fuel production. The problem is that right now what's happening is there are all these directives, but you still have the emissions coming out, right? And then basically what you are trying to do, the engineers are trying to scoop the water out of the sinking boat, which is through carbon capture. So you're trying to capture a fraction of what you are already emitting. Well, obviously it would be way smarter to address the fountain at the back, the fountain being the huge inefficiency gaps that remain unaddressed. So that's avoidable emissions that can completely be avoided, but still have not been. And then huge barriers to decarbonization. I guess I should wrap up very quickly, and I just wanted to say why, right? So the question is probably why. All these industries have been operating for a long time. There's been a lot of investment. Plus, there are big barriers to decarbonization. Like I said, the facilities are deep processing. It's hard. So the technology for optimizing efficiency has remained the same for over the past 40 years. So pinch analysis is basically about reducing the delta between your hottest stream and the coldest stream. But there hasn't been any innovation in that space. And also, there is a lot of permitting restrictions with modifying the facilities. So there are no methods that can actually account for that to make those projects profitable. So what ends up happening is the producers, they have a range of projects to optimize their efficiency, but they end up not implemented because the profitability is not there, and they just are pushed down in priority. So of course, it requires a structure that not only monitors and accounts for CO2 and how much can be actually improved in terms of efficiency, but also rewards the manufacturers with added value. For example, if you become more efficient, you save money on energy that you spend, right? And at the same time, you reduce your emissions. So that's the ultimate approach to profitably decarbonizing, through incentivizing the manufacturers to reduce their emissions through added value. And the DOE actually highlighted that if the efficiency measures that exist right now were cost effective, we could reduce those emissions not by just 30%, as in the scenario, but by as high as 50%. And if you stick around to when I do a pitch later today, I'll show that actually from our data, we see, well, benchmarking data shows up to 34% in the US on average in refining remains unrealized. That's just money that's thrown into the air, about $8.3 billion per year, uncaptured. And I will show you how through our methodology, we've shown that indeed these numbers translate to real life. So actually you can get savings as high as 50 or 60% or even higher. Right, I guess we are out of time, so I'll stop and thank you for your attention, and we'll be happy to take any questions.
Thank you, Nick. And does anyone have any questions that they'd like to ask? Wonderful.
Just a quick one, Nick. Thanks for the presentation. I was wondering if you could wave a magic wand and get some of the things that are stuck unstuck to make more progress, which one would you go with first? What should happen next?
Yeah, what should really happen is there should be a lot of synergistic work, not only between the innovators in, well, speaking, I will address it from the point of energy efficiency, of course, right? Because there's a lot of investment right now into carbon capture. There's a lot of investment into low carbon fuels, but energy efficiency has remained a sort of a darker member of the family of those four pillars, is because the manufacturers are just assuming they've already addressed all the silos that they have, and the ones that are unaddressed are just not profitable, right? I can tell you right now, refiners across the US are making, the profit margin is about 5 cents per gallon. That's how much the refinery is making. In California, there are refineries I've seen that actually, in the past year, the margin was minus 16 cents per gallon. So they are wasting money making fuel. Of course, the gas price is going to go up. So I think there needs to be not only a lot of work with educating the community, but also the people around, right? So just to spread the word that actually, even though we are trying to move away from petroleum, addressing the inefficiencies can dramatically cut down the emissions, and that's how we can take a fast approach, as opposed to waiting for carbon capture or low carbon fuels. I think there needs to be a lot of work with not only the communities, but policymakers as well. Because right now, there's definitely a disconnect with the pressure to decarbonize through electrification and seeing what's actually the fastest way to make impact.
Great point. Anyone have a question? Awesome. I'll journey to you.
Right, thank you for your talk. In terms of the scalability of the energy efficiency, if you were to do it with a refinery and make it work for their particular circumstance, that be scalable and applicable to other refineries in different companies, or large or small?
Absolutely, yeah, that's a great point. Thanks for the question. With new methods, like I mentioned, the gaps exist with any heat-intensive facility. Actually, if you look across, it doesn't have to be a refinery. Chemical production plants, waste to power, waste to heat, power plants as well. Wherever you have a heater and a cooler, you're going to waste some of that heat. Right? So with what Ansel is an energy efficiency research company, what we've been doing is we've been developing the methodology to address and find those inefficiencies and find most profitable ways to address them. So if you can identify it in a refinery, you can easily identify it at any similar plant, refinery or biorefinery. I can tell you, currently refineries transitioning to biorefineries. Of course, the Scope 3 emissions are going to go down because of the moving away from fossil fuels. But they still have to heat the biomass. And that heat is still going to lead to avoidable waste, which means additional emissions. So yes, it's fully scalable across all industries.
Great question. Does anyone else have another question? Wonderful. Someone is delivering a microphone to you.
Do you think that a carbon neutral fuel like hydrogen gas would be a good solution, even though the manufacturing and refining process of hydrogen gas might also take energy? So let's say nuclear power and solar power are not ready to scale for manufacturing, still require coal, right? I mean, it's not to say that we can make this calculation, but do you think hydrogen fuels, for example, would be feasible to address this solution?
Great question. Yeah. If we think about the energy mix, right, as I mentioned, you can think of it in two categories. There is the reliable energy, which is petroleum, which is coal, natural gas. And there is this sort of less reliable and intermittent, which is, solar, wind. Hydrogen is sort of in between, because right now the network distribution is not there. The production perhaps can be scaled, but how easily can you scale the distribution of stations? I've seen hydrogen-powered vehicles on the road, right? But how many stations are there to fuel them? And then also, obviously, there are. So right now, I can tell you in refining, hydrogen is a hot topic. There is obviously green hydrogen, there is blue, there is gray, there are many kinds. One of the most promising ways to introduce hydrogen into the production pipeline is actually to use it to ramp up the syngas. So you capture the CO2 and then you convert that to methanol. And that's how you can basically do carbon capture, as opposed to dumping it underground. You're converting it into a liquid form. And you need hydrogen for that, essentially, either atomic hydrogen or molecular. And there's a lot of innovation there. But using it as a fuel source, you can also think about fuels as low density and high density, right? So the highest density fuel right now that we have, except nuclear, is obviously liquid petroleum products. A great product. But then hydrogen is on sort of a lower density in terms of energy. There are challenges with hydrogen, but it's a promising direction to take.
Great point.
So I always wondered, why don't we see more turbo diesel engines in consumer vehicles that we like you do in the EU? You're just if you go to Europe, you get a turbo diesel BMW, you get like 1,000 miles per tank. I mean, the energy density is much higher. The cost of refining is much lower. It seems like a win-win, but we don't see that in America.
Yeah, I guess it's more of a point to car manufacturers. I guess it's not introduced as much, but we definitely see introduction of lowering scope 2 and scope 3 emissions through blending with ethanol or blending with biofuels. Right now, obviously, we don't have as many 100% biofuels available to fuel the cars. But as you know, California is actually banning petroleum, internal combustion engine cars in 2035. There are going to be no cars sold after that, which will be quite. I don't think everyone is realizing what's coming, but we'll see with that. And I can tell you that right now, the way that manufacturers are getting away from the pressures to decarbonize is actually introducing a little bit of bio feedstocks, but keeping majority of oil production still on site. Sort of a good analogy is, if you think about it, how you eat vegetables with your main meal to sort of, to stay within the limits. But in terms of turbo diesel, I think that would be more of a, there are probably some challenges with manufacturing from the car side.
My understanding is with biofuels is there a lower efficiency, like lower miles per gallon, lower energy density with the
lower
biofuel.
Energy density, that is true. But the biggest challenge, like I said, is scalability. There is just not enough feedstock. If you take all of your cooking oil and all of the vegetable oils that you can get, and of course, which needs to be grown as well, right? All of the tallow, and there are so many companies that are doing that. The production is just, fractions of what you need, actually. And the fuel demand is only going to grow.
Superb questions. Definitely want to continue that conversation during the networking time.